Hey guys, welcome back. Today we're going to be talking all about some more compounds. To start off, we're going to talk about covalent compounds. Now, covalent compounds are going to be compounds between two types of non-metals. In the previous video, we talked about ionic compounds, and that was ions, cation and anion, or metal and non-metal. So ionic compounds are between a metal and a non-metal, and covalent compounds are between non-metals. So talking about covalent compounds is actually a bit of a different way that we go about naming them. The way we do this is through a system of prefixes. So 1 being mono, 2 being di, 3 tri, 4 tetra, 5 penta, 6 hexa, 7 hepta, 8 octa, 9 nona, and then 10 deca. Obviously we can go up as high as we want, but for the pretty much entirety of this course, this is all you're going to be using. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. So when talking about these things, we pretty much just add them to the beginning of whatever compound we're talking about. And covalent compounds, since we're talking about two nonmetals, both things should have a negative charge. And if we're talking about negative charges, it's not really going to be able to cross because we have to have a positive and negative for it to cancel out. Like if we were talking about, I don't know, N with a 3- charge, so nitrogen with 3- charge, and then chlorine with a negative charge, that just equals an entire molecule with a 4- charge. That wouldn't work. So we talk about it in a bit of a different way. So let's say we're talking about something that we all know of, carbon dioxide, CO2. Carbon dioxide is super common. So whenever we're talking about our first molecule, we are going to put a prefix for every single thing except for mono. So in this case, there is only one carbon, so you just write carbon, not monocarbon, not anything else. And then over here, with O2, 2 oxygens, 2 is dioxide, carbon dioxide. Same thing with CO. Carbon only has 1, so it's just carbon. And then over here we have O, mono for 1, monoxide. Carbon monoxide for CO. So let's move on to a bit of a different example. Let's talk about dinitrogen holy crap, I misspelled that. Dinitrogen tetroxide. Now let's talk about another example, flipping it around though. Dinitrogen tetroxide. So when looking at this, we see that we have nitrogen and oxide as our two base words. So we're going to have a nitrogen and we're going to have an oxygen. And keep in mind, we're also always going to have the IDE ending for the second part of our compound. So nitrogen, we're talking about di, so di means 2, so N2. Then tetroxide, tetra is 4, so O4. N2O4 is dinitrogen tetroxide. I know you may be saying we want to cancel these out to find the lowest ratio, find the empirical formula, but for covalent compounds, we do not do that. No matter what your numbers are, it's going to be like that. Like if I gave you, I don't know, something like N2O2, it still is always going to be 2 and 2. If I gave you S2, or not 2, S10O5, you may want to go 2 and 1, but it's always going to be that same exact thing. As I stated in the last video, naming compounds is not something that's necessarily terribly hard, but it does take a lot of practice. There are a lot of tedious little details that do add up and are going to be a lot of easy test questions on your exams and quizzes. I remember when I was taking chemistry, I used to have like pages of just straight naming compounds, like 50 compounds a page, and it was just naming every single one of them, and it's an easy way to lose points if you don't practice it. You have to be really comfortable with doing these things because it is such a fundamental topic for this course. If you can't name a compound later on, it might give you different properties, different masses, different things that would ultimately mess up your answer. All right, moving on to acids. So acids have their very own special, unique way that we go about naming them. And the way that I remember it is by writing down this little chart. So whenever I'm talking about an acid, let's first get into like what an acid actually is. So an acid is something that's going to have a hydrogen ion and then whatever anion over here. So that could be HCl, HBr, HNO3, whatever. It could be any of those things. So when talking about acids, I want you to memorize this chart. I'm going to write it down over here, but I want you to remember it, keep it in mind. If you need to, write it on every single thing you do, every test, every quiz, whatever, and eventually it'll become just mental muscle memory. So whenever we're talking about acids, and just bear with me, I'm going to explain it after, we're going to have ic and ate, per ic and per ate, ite and us, and then hypoite and hypo us. So I know this looks completely confusing and you are like, what am I talking about? Let's get into it. So remember how we talked about in the last video some of those polyatomic ions? The polyatomic ions have specific names. So for example, if we're talking about chlorate, for example, ClO3-, that is known as chlorate. So they have this cool thing about them that depending on the number of oxygens, you can change the name. So let's say we have ClO4 with a minus. That is perchlorate. If we have ClO2 minus, that's chlorite. If we have ClO minus, that is going to be hypochlorite. So as you can see, the number of oxygens directly correlates to the name. So ClO3 is going to be chlorate, ClO4 is going to be perchlorate, ClO2 is going to be chlorite, and then ClO is going to be hypochlorite. And as you can see, per8 becomes per-ic when we're talking about acids. So if we have an H plus with each of these, right? And we're trying to name them all, these all become different types of acids. So if we take our charges and we cross them, it's 1 to 1, so it's always going to be that for this case. But for this case, we have HClO4. And if we look at our name that we're using for our anion, it's perchlorate. So our acid is going to become perchloric acid. So perchloric acid. Not perchlorate acid, perchloric. Perchlorate becomes perchloric. Same thing here. If we have HClO3, chlorate becomes ic, so this becomes chloric acid. Same idea. Down here, chlorite, that's going to be HClO2. That becomes chlorous acid. And then lastly, hypochlorite will be HClO, and that becomes hypochlorous acid. So whenever we're talking about naming acids, it's not really anything that's super, challenging. It's just remembering the names. So what I do and what I recommend you guys do is just writing down this chart. Whatever you need to do to memorize these names, the transitions from, different things, it helps. So when talking about chlorate to chlorite and hypochlorite and perchlorate and everything, and changing between those names and transitioning, remember that we're always keeping the charge. And whatever your number of oxygens is, if you're dropping one, you just drop one name. So let's say we're talking about, for example, sulfate, SO4 2-. And that's sulfate. If I want to get to sulfite, it's the same idea. SO3, charge stays, that becomes sulfite. And when naming those acids, it's the same idea. So we have our H+, and it becomes, we take those charges and we cross them, it becomes H2SO4, and over here, H2SO3. When talking about our sulfate, sulfate becomes sulfuric. So this becomes sulfuric acid, not sulfic, sulfuric. Whenever you have any sort of sulfate, phosphate, you're going to pretty much put in the original element. So sulfate is based with sulfur, sulfuric. Phosphate is based with phosphorus, so phosphoric. It just sounds a bit cleaner. Not really sure why we do it, but it's just something that we do. And then moving down to sulfite, sulfite becomes sulfurous. Remember that sulfur, sulfurous acid. It's all the same thing, no matter what type of compound you're using. It's just important to memorize this chart and then how to get between the different names. One more thing with acids is we've only talked about ways to name them with polyatomic ions. So let's say we have something on the periodic table, like just a simple anion, right? Like chlorine or bromine or sulfur, right? So we need to add our H+ to each of them. and we need to find our charge for each of these ions. Chlorine is group 7A, has a -1 charge. Bromine is also group 7A, has a -1 charge. And then sulfur is a group 6A, so it has a 2- charge. And we just cross over our charges for each one. So we get up here HCl, HBr, and down here H2S. So when naming these, you may be saying, okay, well, there's no way to say I to anything, so we have a different way of naming it. So whenever we're talking about just a simple anion and hydrogen, we say it's a hydroacid. So we name this as hydrochloric acid. This one is hydrobromic acid. And this one is hydrosulfuric acid. Remember, sulfur, sulfuric, same thing. Hydro, whatever anionic acid. So hydrochloric, hydrobromic, hydrosulfuric, hydrophosphoric, hydroiodic, whatever. No matter whatever basic anion you're using, if it's on the periodic table, it's hydroic. But yeah, that's pretty much all for acids. Let's move on to our next topic. So when talking about acids, they are typically, you're more, based on a scale, they're on one end, and then on the other end, there's this thing known as bases. So talking about bases, the only thing that we really need to know is what OH is. So when talking about bases, we have this thing known as a hydroxide ion. And all it is OH minus. So when we're talking about different types of bases, we need to just understand that this OH, the same way as a polyatomic ion is going to have the entire O and H is going to have a -1 charge. So if we're talking about something, for example, sodium hydroxide, sodium being group 1A is going to have a +1 charge, and OH will have a -1 charge. You cancel these charges with each other, bring them to the other side, you get NaOH, sodium hydroxide. If we're talking about barium hydroxide, barium being group 2A is going to have a 2+ charge, and then hydroxide has a -1 charge. So we take our charges, bring them to the other side, we get Ba and then OH2, barium hydroxide. Besides that, pretty much that's it for naming bases, but there is one cool thing that I can kind of show you guys. Might impress your teachers if you know this, but when talking about acids and bases, there's a scale. So it's known as pH. There's a 14-point scale, so it goes from 0 all the way to 14. And, well, actually, technically 1, but 1 to 14. And in the middle of that, there's 7. 7 being completely neutral. And the thing we typically associate with being number 7 is water, H2O. And as we talked about other acids, acids are the addition of a hydrogen ion, and our bases are the addition of an OH ion, a hydroxide ion. You may see where I'm going with this, but if we take our H plus and our OH minus, we get HOH or H2O, which is water. So if we take our most basic thing and our most acidic thing and we combine them, we get perfect equilibrium in the middle with water. It's not really important for right now, but I think it's a pretty cool thing that most people don't really understand. It'd be something cool you could tell your teachers, tell your classmates, whatever, but it's definitely something I find to be quite interesting. All right, last topic for this video, hydrates. So whenever we're talking about hydrates, there is a base word that you may here and there. Hydrate, water. Whenever you hydrate your body, you're giving it water. Same thing in chemistry. If you're hydrating a compound, you're giving it water. So there are countless different types of ways we can go about this. But the way that's most common is by doing the ionic and then putting a dot and then prefix hydrate. So when talking about prefix, all we're doing is we're giving it the prefix from the covalent compounds: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Ionic just means ionic compounds, whatever ionic compound that may be, and then you're pretty much just putting dot, however many waters. So let's start with a little example. BaCl2 and then dot 2H2O. So looking at this, BaCl2 is barium chloride. And it is 2 waters, so dihydrate. All this is saying that we have a barium chloride with 2 waters attached to it. Now let's work in reverse. Let's talk about magnesium sulfate heptahydrate. Magnesium sulfate heptahydrate. So magnesium, being in group 2A, is going to have a 2+ charge, so Mg 2+. And then sulfate is one of those polyatomic ions you just have to know. It's going to be SO4 2-. And then heptahydrate being 7 waters, 7H2O. Now let's combine everything. Let's take our charges and we're going to cross them, and we get Mg SO4 in parentheses 2 7H2O. Magnesium sulfate heptahydrate. But yeah, that's pretty much it for naming compounds. If you missed the last video, ionic compounds are in there. You may have been a bit lost with some of these different types of naming things if you missed that video. So it could be a good watch. And like I said before, it's really important when talking about nomenclature that we do practice these things. It is tedious. It is, a lot of little steps that do overall mess you up if you do get them wrong. It's going to be practice, practice, practice. I'm going to attach a bunch of practice problems down below. Please do them. It's going to help you with your quizzes, your exams. But I can't stress this enough. This is probably one of the most important things you will learn how to do in this class. It's going to be on every single test, every single quiz. You are always going to have to name something. So get comfortable with it. Like, do the practice problems, do your own practice problems, like watch more videos, do more, work on this. This topic is super important. Naming compounds is the basis of all chemistry. But I hope you enjoyed. I hope this helped, and best of luck to you all.